Ja, hi allesammen. Good morning, everybody, and Happy New Year. Welcome back to our webinar series God Forskermorgen, which is brought to you by cooperation of Multiconsult and Hydrosen. Once a month, a researcher from Hydrosen comes and presents the latest research related to our industry. And this time we have Hossein Ehya. He's going to take us through how condition-based maintenance can save costs. If you will have questions during the presentation, please write them to the Teams chat window and we will take them in the end. Please go ahead, Hossein.
Okay, good morning, everybody. Thanks for attending this webinar. What I'm going to present is how condition-based maintenance can save the cost in industry. The topics that I will cover in this presentation, I will I will explain what is periodic maintenance, and then what is condition monitoring, why do we need condition monitoring, and afterward I will move into different type of faults in electrical machines. And of course, the researchers have been working for more than two decades on condition-based maintenance. So definitely there are many methods and approach that industries can utilize. But what is the limitation of these methods, and what is our solution for that? As you all know, electrical machines, they are working based on Maxwell equations, but they are not smart enough, intelligent enough to tell us when will they fail, or when is their periodic maintenance time. So if there is any type of failure in electric machine, they will not give us a notice before, so they will fail. What is the role of periodic maintenance? Engineers, technicians, based on the industry timeline. For instance, every 6 months or once a year, they inspect the electric machine, generator, motor, and if they can find any sign of fault in an electric machine, they will stop it and they will perform the maintenance. But if they are not lucky to inspect the machine before the failure, then it will fail. But what is condition monitoring? What we are doing, we are similar to medics. The only difference between us and the medics is our case study. Our case study is electrical machine. We also have the checklist. We need to record some signal from the machine, and we need to analyze these signals. And then based on our analysis, we can conclude the machine is operating in a healthy case or it has a fault. And if it has a fault, which kind of fault it has, where it's its location, and how is its severity. But why do we need condition monitoring? Why we cannot use periodic maintenance, which is the most dominant approach in a maintenance industry? First of all, we want to reduce the cost. According to a report in the United States, they spend $2 billion per year for maintenance of electrical machines. And they spend 70% of this money only for electrical machines that do not have condition monitoring system. We estimated that this amount of money for Norway, it is around 300 up to 400 million NOK per year. So by using condition-based maintenance, we want to reduce this cost. The second reason is we want to avoid unexpected stoppage of the machine. Imagine that you are producing electricity and it is in a high season. And if there is any type of fault in the electric machine, as I said, it will not give you a notice. It will stop and you cannot produce electricity. And it means that you are losing money. And it is the case for many different application area, like a wind farm, oil and gas platform, and so forth. The third reason is we want to reduce the maintenance time. If you are using condition-based maintenance, and if this condition-based maintenance, if you know which kind of fault you have and where is its location, then during the maintenance period, you don't need to inspect every single part of the machine. You will only need to check the specific part and repair it, and that's it. So by having condition-based maintenance, you can reduce the cost again. In some application area that are located in remote areas, like oil and gas platforms or wind parks, for wind parks, they are located in a place with a harsh environment. So it is very dangerous for the electricians or engineers to inspect electric generator, to go up into the mill and check the generator in these wind parks. So we need a condition monitoring system to tell us in advance that your machine will fail, and then they can take action to stop the machine and perform the inspection. In some application area which is related to human being, like electric aviation, electric cars, hyperloop, electric ships or ferries, safety is a key point that forces us to use condition monitoring. Since 2010 until now, there are several reports that due to the failure in electric powertrain in electric car, especially in Tesla cars, there are severe accidents. So safety is a key. So we need to utilize condition-based maintenance to avoid any kind of accident. And imagine in electric aviation, safety is really crucial. So we cannot really trust periodic maintenance for this kind of application. Now let's move into the next part, which is a different type of fault in electrical machines. We have different type of electrical machines, induction motors, permanent magnets with a different type of topology, outer rotor, inner rotor, or we have a salient pole synchronous machine. We have different other type of electrical machine. But the point is, the faults are common among all these electrical machines. We can categorize faults in electrical machine into two groups: short circuit in the stator winding or in a rotor winding, mechanical fault like static eccentricity, dynamic eccentricity, misalignment, broken damper bar, faults in the core. All of them are categorized as a mechanical fault. Each electrical machine, it consists of two parts. One is the stator, which is this part, and one is the rotor, which is the rotating part of electric machine. Okay, let's see which kind of fault which lead into what is the consequence of having fault in electric machine. By having a short circuit fault in the stator, this is the stator which consists of stator winding and stator core. The most prevalent type of fault in the stator part is the short circuit fault in the stator winding. By having short circuit fault in the stator winding, which can be due to different reasons, in a best case, you need to repair only the stator winding, but most of the time it can damage the stator core. So it means that if you have a fault, then you need to replace both stator core and the stator winding. Rotor in salient pole synchronous machine, it has each pole, it has multi turns, and we could have a short circuit in the rotor field winding. But since the voltage level in this this type of winding is low, even by having few shorted turns, the machine can operate for a few months or maybe a year. The next type of fault is eccentricity faults. we assume that for a healthy electric machine, the rotor must rotate exactly at the center of a stator. So the air gap is identical in any point. By having static eccentricity fault, on the one side, we have smaller air gap, and on the other side, we have a larger air gap. But this is constant, so this smaller air gap is always close to one side of the stator. But in the case of dynamic eccentricity, this small air gap will start to rotate inside the stator or air gap. The worst case of having eccentricity fault is the misalignment. Since in the case of misalignment, the air gap length is vary along the axial axis of the machine. Detection of this fault is really difficult. Okay, if you have eccentricity or misalignment, what will happen to the machine? In a worst case, the rotor can touch the stator core. And as you see, it can damage both stator core, stator winding, rotor core, and rotor winding. What does it mean? You need to replace the entire machine. The next type of fault is broken damper bar or broken end ring fault. This type of fault is mostly prevalent to induction motors or salient pole synchronous machine. What you see here, these are the damper bars, and this is the end ring, and these are the connecting point between the end ring, as you see here. In a case of having a broken damper bar fault in the induction motors or in a salient pole synchronous machine, if you're lucky, you only need to repair the rotor, but in a worst case, it can damage the stator winding. So you already know which kind of fault we have in electric machines. And let's see which kind of methods or approach we already have to utilize for a condition monitoring. What you see here, we have different type of methods because we have different type of signal in an electric machine. It can be magnetic field, we have voltage or current, we have a vibration, we can use thermal monitoring. These are all kind of commercialized method that you can utilize for condition monitoring. But these methods, they have some limitation. Let's see what are the limitation of these methods. We can categorize the condition monitoring methods as two. One is online and the other is offline methods. In the case of offline method, you need to stop the machine. Sometimes you need to remove the rotor, like in the case of core fault detection, and then perform the inspection. Or sometimes you need to measure the resistivity or inductance of the phases, and based on that, maybe you can detect the fault. But these methods are not favorite of industry because you need to stop the machine. They cannot produce, they cannot operate their the machine in their production lines. So new methods based on online methods are developed. We can categorize also the online methods into two groups. One is invasive methods. What is invasive methods? In the case of invasive methods, we need to put the sensor inside the machine. What you see here, you need to remove the rotor, and then you can install the sensor, what you see here, like Hall effect sensor or surge coil on the stator tooth. Also, this method, this signal, the air gap magnetic field, can provide a very detailed informative signal to us, but its main problem is it is invasive. So especially for large electrical machines in the hydropower plants or in wind parks or in oil platforms, it is very difficult to convince the industry owner to remove their rotor and stop the production. The other point is these sensors are very fragile. Even if you can install the sensor inside the machine, after a couple of months, it will start to fail. So you need to replace it. So researchers, they came up with the idea of utilizing non-invasive methods. It can be measuring the voltage or current of the machine utilizing PT or CT, or you can use accelerometer to record the vibration. Also, these methods are non-invasive, but the main problem with these methods is they are not sensitive to the faults. It means that you need to have a certain amount of or certain degree of fault in a machine, like 30%, 40% eccentricity, or a couple of shorted circuit, then you will see some variation in these signals. Otherwise, for earlier stage detection, which is crucial for some application like electric aviation, electric cars, you cannot trust these methods. The third limitation of previously developed methods, they are expensive. Let's assume that the data acquisition system and the analyzing methods are the same. And let's only consider the uh, comparison between the sensor cost. If you're going to use air gap magnetic field, you need to use Hall effect sensors. And for a good or comprehensive condition monitoring, you need at least 8 sensors. Each sensor, it can cost 10,000 NOK, so you need 80,000 NOK only for Hall effect sensors. In the case of using voltage or current, you need 3 sensors, and for a lowest price, it is 10,000 NOK, so it will cost 30,000 for each of them. And then for accelerometer, even if you want to use 3, because most of the time we need more than 3, but for the lowest case, we need 3. Each of them, it will cost 15,000, so 45,000 for 3 of them. For a thermal camera, for a good one, it will start for the lowest price from 100,000 NOK. For a partial discharge measurement, this one is the worst case. It costs 500,000 NOK, and you have to install it permanently on the machine for online monitoring. And in the case of offline monitoring, yeah, you need to perform the test in offline mode. The other limitation is we need a prior knowledge of the machine. What does it mean? It means that in a lab, we have a healthy machine. We can operate the machine, then we can record the signal and analyze it and save it. And then we apply different type of fault. For instance, in this case, we can remove the damper bars and we can emulate the broken damper bar fault. And we can perform the test and we can record the data again. And by comparing the faulty case with the healthy case, we can realize that we have broken damper bar fault. But the question is it really possible to have the healthy machine data for asynchronous motors or generators that have been operating for a few decades in power plant or even electric motors in industry? Is it really possible to have the healthy data of these machines? The answer is no. So all these developed methods, it is only good for academic publication. The last limitation is the signal processing method, the way that they analyze these signals. They are not informative. It means that in a case of any type of fault, these are the sidebands or harmonics. In the case of any type of fault, short circuits, broken damper bar fault, eccentricity, all of these harmonics will appear. So it will not give you any information that which kind of fault you have in a machine, or even if the machine is operating in a healthy case or not. Maybe you want to say, let's define a threshold, but these thresholds, depends on a power rating of the machine and its topology. So maybe for a 100 kilovolt amp machine, it is minus 40 decibel, but for 100 megavolt amp machine, maybe it is minus 30 or minus 50. Okay, what is the solution for that? We proposed a method. Our method, it is online, so you can install the sensor even during the operation of the machine. You don't need to stop the machine. It can give you, it is informative or signal processing method. It means that it will give you detailed information, which kind of fault you have, where its location and hides its severity. It is sensitive, so it's not like a vibration or current and voltage measurement that we can detect one interturn short circuit fault or 5% eccentricity. The last one, which is the most important for industry players, it is inexpensive. I will explain in detail. What is it? What is the idea? We have a magnetic field outside the machine. So, but the point is, this magnetic field outside is very weak. It is in the order of micro Tesla. So, by utilizing, we developed our own custom-made sensor. By utilizing this sensor, we can capture the magnetic field outside the machine. This is what you see as a output of this sensor for a 22 megavolt amp synchronous machine in power plant. But the point is how we can extract information from this signal. We used time and frequency domain advanced signal processing method, which is based on time and frequency domain. There are some definition. Each of these, as you see, let me just zoom it. Yeah. What you see here, each of these that I call it as a stock, it represents one rotor pole. So we have 14. So 14 of these, it can represent one mechanical revolution of the machine. For instance, for this representation, it is for an 8-pole machine. So in a case of healthy operation of the machine, you have 8 of these stocks, which represent one mechanical revolution or the entire rotor poles. As you see, for a healthy case, we have uniform pattern. The intensity is the same. By introducing interturn short circuit fault in the rotor field winding, the faulty pole, its amplitude and also its shape is completely different. By introducing or emulating the dynamic eccentricity fault, we have completely unique pattern. What about static eccentricity fault? The static eccentricity, you cannot detect this fault using vibration, voltage, and current. So it is impossible to detect by utilizing those methods. But in our case, only we need 2 sensors on 2 sides of the machine. On the one side that we have a larger air gap, the amplitude will decrease. And on the other side, which we have a smaller air gap, the amplitude will increase. So in this case, we can even detect a static eccentricity fault. What about broken Gamberfault fault? This one is very tricky, especially in synchronous machines. Utilizing these methods, we can detect a fault both during transient operation of the machine and also during a steady state operation of the machine. I said our method is very sensitive. We can detect one interturn short circuit fault. What you see here, in a case of healthy operation, by introducing one interturn short circuit fault, the intensity level is increased about 11%. So definitely you can even detect one interturn short circuit fault in the rotor field winding. I said our method is inexpensive because the cost of our sensor for mass production, it only costs 100 NOK. So even in the case of utilizing 8 sensors, it will cost 800 NOK, not 80,000. Okay, maybe you want to ask me that is it possible to detect, or does it has the abilities the other methods has? The answer is, if you are looking at the fault detection, this part, I define different type of faults like dynamic eccentricity, static eccentricity, misalignment, short circuit, and broken Gamberfault fault. Only 2 methods. One is air gap magnetic field, and the other is stray magnetic field, which is the method that we are utilizing. Only these 2 methods can detect all these faults. The next point is the only difference, as you see here, is the level of difficulty in implementation. In a case of air gap magnetic field, we need to stop the machine, we need to remove the rotor, put the sensor inside again, and remove the rotor back. But in our case, you need to mount a sensor outside the machine, so you don't even need to stop the machine. And the main difference is the cost. So our method, it has all the abilities that all of these commercialized method has. And the main difference is our cost and the ability of our method to detect all these faults with high sensitivity. We want to go even further and reduce the cost, because when you have these, you need someone, you need to educate your technician or engineers in industry, or you need to record the data and send it back to the consultancy company, and then they can perform all these analysis. By utilizing AI techniques, we can reduce the cost even further, and the method will tell you the machine, is it operating in a healthy case or not, and if it's operating in a faulty condition, which kind of fault you have, where is its location, and how is its severity. So it will give you a very comprehensive report, and that's it. And regarding our case study, first one, I have applied all these all these faults to this 100 kilovolt amp salient pole synchronous machine, which resembles a typical Norwegian hydropower plant generator. You can emulate, you can apply different type of fault, like short circuit fault. You can remove the damper bars fault to have broken end ring or broken damper bar fault. Even you can rotate, you can move the stator core to the right or left to emulate the static eccentricity fault. And we were able to detect all these faults with very high sensitivity in a lab. The next is, because most of the time you can come up with very good idea, you can get really good result in a lab, but when you are going to use it in reality, it can't work. So I had a chance to apply my method to 22 megavolt amp machine in one of Norwegian hydropower plants. It has a complete different topology, different power rating, and we were able to detect a fault in this machine. It has two faults, dynamic eccentricity and short circuit fault. So it indicates that our method, it is even able to detect two faults at the same time in this machine. The next case study is this electric machine, this generator with 40 megavolt amp power rating with 16 poles. In this power plant, they have 4 units. So we were able to check how is the noise and environment impact our signal while the other 3 units were operating. And in this case, we were able to detect the faults, and we realized that the noise and the environmental factors do not really influence or measuring signal. So this case study was also successful. If I want to summarize my presentation, for companies which they are working in a maintenance industry, if you want to survive in future, if you want to still become a role player, you need to switch into condition-based maintenance. Many companies, as I know, as I had a discussion with them, they are looking for a solution to switch into condition-based maintenance. And if you are reluctant to use it, sooner or later, you will not survive. So condition-based maintenance is the only solution for maintenance industry in the future. Thank you all. If you have a question, please ask me.
Thank you very much for an interesting presentation, Hossein. It looks very, very promising, your method and the results of it. It was as well really good overview for us not so well known with the subject, that and it's not valid just for generators. It's going to be high likely as well in the mechanical industry and other electrical machines, that the condition-based maintenance has a lot of potential for future and should take over the periodic maintenance.
Yeah.
Questions. So far, there's only one question in the chat. It's from Mats Bilstein. He's asking, is the estimated cost only for EM, electric machines in hydropower? You mentioned 300 to 400 million NOK estimate in Norway.
No, it is for the entire electrical machine. This is based on estimation, but it includes any type of electrical machines in industry. It can be in the oil and gas platform. It can be in hydropower plants, in wind parks, and so forth.
You as well mentioned from the study in USA, 70%.
Yeah.
That was what is spent on electrical machines that do not have the conditional monitoring.
Yeah.
To imply that all of the 70% is cost which wouldn't have to be invested, or it's not.
Yeah.
It's of course not invested in the right time, but
the point is for periodic maintenance, sometimes you need to replace, for instance, bearings in this period of time. So even if it's operating in a healthy condition and it can work maybe for next 1 year, but based on this periodic maintenance, they have to replace it. So this is some of the costs that you can reduce it by utilizing condition-based maintenance.
Another question from Mats Bilstein. What is the definition of a successful field test?
I can say if you can detect the fault in the low severity fault, and if you can detect, first of all, if you can detect the machine is operating in a healthy case or not. And then the next step is if you can detect which kind of fault you have and where is this location. Because these two factors, they are the key factors that many of these methods that have been proposed until now, they are not able to tell us. So for many of methods, like for instance vibration, which is the dominant method for fault detection, it will only tell us the machine is operating in a healthy case or not. But if you want to have a successful field inspection, you need a method can give you faulty or healthy, and if it is faulty, which kind of fault you have, where is its location, what is its severity, and how long time do you have until failure.
Thank you. Did you receive any feedback while you were doing the field tests on the two stations, Kalvedalen and now power plant, from the owners?
Actually, these two power plants, they had a inspection from a consultancy company, and they only just told these companies that it has a fault based on vibration analysis, which is the trend analysis. It is above this value based on IEC standard, so it has fault. But we only provide them with a detailed information, and as I know, I think they have a plan to stop the machine, this machine for this summer for Kalvedalen, if I'm not wrong. So based on their inspection, I think they can approve that our result is correct or not.
Okay, very good. One more from Mats. Each machine is unique. Do you take a fingerprint and consider that as normal operation?
The good point or the novelty of our method is you don't need any information from machine. So regardless of their power rating, even their specification, you can apply this method. What you need, what you need is only, what you need is only the number of poles in a machine, which you can easily find it on a nameplate data. So you don't really need any information from the machine, regardless of their power rating. It can be any type of electric machine, any type of fault in electric machine. If you have the number of poles, you can perform this test, and it will give you a detailed information that you have a fault or not.
We have a question from Haugen Beate. What is the requirements for the data logger?
What we used is the oscilloscope, but the only requirement is you need a data acquisition system that you can record the data with a sampling frequency of 10 kilohertz. That's it. So it can be oscilloscope, or it can be data acquisition card, whatever you have. So this method, you can integrate it into your existing system. So you don't even need to invest on a data acquisition system.
Prajwal asked here, is it possible to share your slides? There's going to be recording of the presentation available. Any more questions? While you were doing your PhD, did you as well get into a lot of discussions about other types of or other subjects of this monitoring, for example, on mechanical parts of the power stations?
You know, the main reason of having a dynamic eccentricity fault is the faults or failure in the B-rings. So you can detect the B-ring related faults by using these methods. So if you see any kind of any kind of pattern similar to what you see here for a dynamic eccentricity fault, it is related to mechanical fault. Or a broken damper bar fault, this is also categorized as a mechanical fault. But if you have any specific type of fault, if you can tell me, then I can tell you that it is possible to detect it or not.
Yeah. No, for now it's quiet in the chat. Let's give it another little bit. We have 5 minutes, which we still can use. But if there are no more questions, then I would like to thank you, Hossein, for the presentation.
Thank you all for attending this webinar.
And please remember to join again next month. We are planning to continue with the Go Forske Morgen series whole 2022. Thank you very much.
Perfect. Thanks.
Have a good day.
Bye.